Great. All right, thank you guys for coming. This is the Applied ZK Constructions 1 lecture. This is the 10th lecture of the ZK IAP class. If you want to ask questions, ask on Zoom. The link is there. Feel free to also just interrupt in the middle. It would be fun if there was like, if you don't fully understand something yet, just like feel free to blurt out, be like, wait a second, where did that come from or something? And it'll be nice to have more of that dialogue and us going over it. Feel free to come to me afterwards or DM me afterwards. I'll be around. The slides are also linked on zkiap.com and in the Google Drive. And if afterwards you're going through the slides, you didn't fully understand something, feel free to just comment on the slides. I get a notification and I can respond directly to that as well. Cool. So this lecture is going to be a little bit of a shift from some of the previous lectures. In the last maybe 1 or 2 weeks, we've been going super deep into the theoretical, how does Planck work? How do these elliptic curve operations combine together and give you zero knowledge? And now that we've kind of built up an understanding, which kind of concluded with the Planckathon, where we've implemented this system end to end, maybe now it's time to discuss, okay, we've seen all of the math and all the theory behind it. How do we extend this to actually use these things and build interesting and meaningful applied ZK applications on top of it? So how we're going to do this is we're going to go through some constructions in roughly increasing order of complexity. We're going to start with super simple ZK message board, some extensions, hey anon. We're going to go into what nullifiers are and how that unlocks some new interesting primitives. Then we're going to try to add Ethereum in and try to combine Ethereum and nullifiers in interesting ways. And then we're going to shift a little bit more to the ZK proofs in the wild and how can we make ZK proofs about things that aren't related to Ethereum and aren't related to the primitives that we have before. And so to understand this, you actually don't need much of the super theoretical buildup from the last week or two. We only need basic circuit comprehension. So if you came to Circom Lecture 1, you'll understand that. If you didn't, I'll also go over briefly for the relevant parts. And basic cryptography, so Merkle trees, hashing, and signatures. So just to get a sense of if I need to go over it or not, can you raise your hand if you're familiar with a Merkle tree and how that works? OK, that's everyone. Great. If you're familiar, OK, that means you have to be familiar with hashing. If you're familiar with signatures, like cryptographic signatures. OK, also everyone. Great. OK, so I will skip those. Cool. So we'll start with a super simple construction, ZK message XYZ. And the intuition we're going to try to get is how do we have simple group membership and message posting? So the idea is that this primitive, this website was built maybe about a year ago, allows you to post messages on behalf of a group and attach a ZK proof of membership with each message. So what are we doing? Well, normally, if you're trying to post online, you have complete anonymity or you have complete doxedness. Everyone knows exactly who you are. And if we want to unlock this new thing in the middle, like pseudonymity, like partial anonymity, the way we can get that is we can prove specific properties about ourselves. So one example property we can prove is I am part of this group. And this isn't complete anonymity. People still know you're one of these, say, 10 people, but they don't know exactly who you are. And so these kind of ZK proofs allow us to create this, select these points between anonymity and non-anonymity, and we kind of call that pseudonymity. So OK, so how does this work? So the idea is that when someone's signing up for zkmessage.xyz, you can see there's kind of two parties here. There's their computer, and there's whatever database that can be the blockchain, a cloud, a server, a website. The user can generate a hash of their secret, and they ensure that no one else knows that secret string. And in the database, they put the hash there. So you can see that on Joel's computer is the only place that the secret string 9j, et cetera, is kept. And the public hash is public to everyone in the database. And in this example, we'll have one group. So maybe Uma generates her hash and adds it to the database. And in this example, we have one group with Joel and Uma that people are trying to prove membership in. And you could extend this. You could have multiple databases with multiple groups. But for simplicity, we'll consider just one group. So what happens when Joel is trying to send a message? So now this is kind of the Circom pseudocode. And you can imagine that one thing he can do is he can input all of the hashes that are currently in the database. So namely, this will be 75, blah, 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 6h, blah, blah, blah. These are all the hashes. The message that he's trying to post, so hi, and Joel's secret. So this is the 9j, 46, et cetera, that when hashed gives you Joel's number in the database. And so you'll notice that in Circom, some things are public, some things are private. and there's some logic down here. So what exactly is going on here is that CIRCOM will, and this was kind of gone over in the lecture, but I'll give a brief refresher, is that what CIRCOM is doing is going to take all of this logic, and it's going to spit out a proof. And this proof will be like a collection of random numbers, basically elliptic curve points, that only verify if this logic holds for the public inputs that are attached to that proof. But the private inputs are not revealed anywhere. And so you can imagine, in this case, what Joel is trying to prove is that for one of the hashes in the set, his hash matches that hash. And you just verify that at the end, there is one such match. And this allows Joel to basically prove that he is one of the members in this set. When he publishes a ZK proof, we know that only someone who knows either Uma's secret or Joel's secret must have posted this message. So this is kind of close to what's happening, but with one small detail, that there's no such thing as an if statement in CIRCOM. You can't do like conditional program branching because of the way that the elliptic curve operations work. So we slightly changed that to this. And what this logic is doing, you'll notice, if you think about this for a second, is more or less the exact same thing. We have basically our list of hashes, 0, 1, etc., and the hash of our secret. And we're just verifying that one of these terms has to be 0, which means that we are one of the hashes that were in the database. And so this basically allows Joel to prove that he's in the database and attach a message to the ZK proof that he publishes. Cool. So that's a super simple construction. Were there any questions on that construction? Because it's kind of critical we understand that before we move on to more complex things. Yeah.
Can you say more about how that's been used?
Yeah. So the idea is that this proof will output some proof signals and the public outputs, which are the public inputs. And these can get sent onto the website, onto the server, onto the blockchain. Anyone can read this proof, verify that, in fact, this corresponds to the code that is public. And they can look at the public inputs and correspond that these public inputs look correct. And this proof can be consumed kind of anywhere. And we'll go into detail with some way that you can consume this kind of thing in a smart contract, for instance. Does that kind of answer the question? Sort of? OK, cool. Great. So we're going to slightly extend this primitive. And we're going to, instead of using hash of secrets, we're going to try to use public and private keys. And so the construction is going to be quite similar. And one instantiation of this is hey anon. And basically what it allows you to do is post on behalf of a list of Ethereum accounts by also publishing a ZK proof that your message comes with a valid signature from one of those set members. So it's kind of a very similar scheme to the one we just discussed, but instead we use public-private key cryptography. So the sign-up phase looks very similar, except instead of joining with hash of secret, you join with a public key. And implicitly, Vivek is the only person who knows his own ETH secret key. As more people join, they get added to the database of the group that we're trying to prove membership in. Now, what is Vivek going to send as his ZK proof? It's going to be very similar. You'll notice that many of these are very similar to the previous proof code that we saw. I'll give people a moment to just take a peek at this. But the idea is that the public keys from the database will be passed in to our proving function, match the public keys that we're trying to prove membership in. We also pass in our message. This message is going to be public. Say it's something like hi. We're going to have our private input, our public key. This is a little strange. Why is our public key a private input? It's because we don't want to reveal which public key we are. We want to say we're one of the public keys in that set, but we're not going to tell you which one we are. So our public key becomes a private input to the ZK snark. Then we also attach a signature of that message. So Vivek, inside his wallet or inside his secure enclave, will sign this message hi with his secret key. And so he generates this signature. And the signature can be verified with the public key, which is exactly what we do inside the ZK circuit. So what is our circuit doing? It's going to verify the public key is one of the public keys in the set of the database, exactly like we did with the ZK message example. And then we're going to verify that the signature of our message, along with the public key, that is the private input here, in fact verifies correctly.
Would the signature of the message also have to depend on the message?
Yep, the signature of the message depends on the message.
Wait, sorry, then I think the message should also be different.
Yes. Message is an argument to verify. It's verifying that the signature is of that message.
You should write
Precisely.
that.
Yes, I will add message as an argument to signify, to verify.
Okay, cool, thank you.
Cool. Now there's one small detail here which we kind of want to avoid. One thing here is that our database can get very, very large. It can be like millions of people potentially. And so this argument we have here, where we're passing in every single one of these public keys in the database, is going to get untenable. It's not possible for us to pass in like millions of arguments into the ZK proof. And so we need some way to reduce this, like the number of arguments we pass in from n arguments to ideally something asymptotically better. Yeah.
So you say sign and verify, but do you actually use like signature scheme or you just like hash?
Yeah, so in this case, we're actually using like the ECDSA signature scheme on Ethereum, and we've implemented, I think a number of people at Xerox PARC implemented the verification of an ECDSA signature inside CIRCOM, which allows you to do this kind of wrong field arithmetic to verify this signature.
I see. So I can sign with my Ethereum key.
You sign with your Ethereum key, precisely. Cool. So okay, so what is the way that we address this improvement? Is we, instead of passing in the entire list, we pass in a Merkle tree. This allows us to pass in a single value, no matter how big our tree is. And our database is now structured, instead of just as a list, as a Merkle tree. And so you'll notice the thing that changed is that we add our Merkle root, which is then also much easier to verify. We only have to verify one value. And in addition, we'll pass in a Merkle path. And so what Vivek can do is, if he's trying to make this proof, he can look at this database, figure out the Merkle path that corresponds to his leaf position, use that as a private input, because if you reveal the Merkle path, then you reveal which leaf you are. So that has to be private. And instead of checking that product that we had before, we check that the hashes of the Merkle path all the way up are, in fact, corresponding to the Merkle root. And there's a detail that I omitted here, which is that the Merkle leaf might change whether you're on the left or the right. But the gist of this is still correct, that you're hashing the public key with each of the values in the Merkle path one after the other. And then you just have to verify that that's the same as our Merkle root.
Wait, so does HeyAnon use Merkle tree or the product?
Yes. HeyAnon uses the Merkle tree because the product thing doesn't work if you have too many people. So the actual thing in production is much closer to this. Cool. So are there any questions, by the way, so far on HeyAnon? Or OK, great. So now that we've gone over these two basic group membership constructions, we've seen a number of properties that they have. So ZK message, we saw hashing a secret and set membership. With HeyAnon, we saw signature verification and Merkle paths. But there are use cases in which we want this additional thing called a nullifier. And this term was coined by Halo2 many years, or by Zcash many years ago. Same people that made Halo2 and the various flavors of Plonk that we've seen the last week or so. And what does a nullifier mean exactly? There are cases in which you want to nullify the ability for users to do an action twice while staying anonymous. And so the idea is that you can publish this value, which is this nullifier, that stops someone from acting with a protocol twice and keeps them anonymous. OK, so we'll try to go over these two constructions of semaphore and tornado cache and explain how exactly nullifiers work. So OK, so what is semaphore? It allows you to do kind of a similar thing to what we had before. So you can do group membership in some list of hashes, along with an anonymous identifier that stops you from double claiming or double posting, or at least, in the worst case, will correlate you across all of your posts. And so what exactly is this nullifier? How is it calculated? OK, so now when people sign up for semaphore, it's going to be slightly different. You can imagine WeiJay might join the semaphore group with their identity hash of, instead of a secret, 2 secrets. So we just split the secret in half. And secret is composed of a part called a nullifier and a part called a trapdoor. And WeiJay, just like the ZK message construction, keeps nullifier and trapdoor secret. And so you can see in the database that the root is still there, and the leaf is this new leaf that he's added, which has the hash of the nullifier and trapdoor. And this represents his public identity. And similarly, other people can join the database. They can post their identity hash, keep their secrets local on their computer, and the Merkle root of the database can update. OK, so what is the thing that we're actually going to prove when we send, say, a message on behalf of this group? So the idea is that I'll explain the exact code in the next slide, but the high level is that this person, say WeiJay, instead of sending just their message and a ZK proof, is now going to send the message, the ZK proof, and this nullifier. And this nullifier is going to be like a hash of their n1 value, so this nullifier value, and the group that we're in. So you can already kind of get the query that we're answering, kind of the topic that we're posting about. So this is like different than the actual group that we're part of, right? So you can imagine that as long as this query, does pineapple belong on pizza, remains the same, no matter what Weijie says as a message, this hash will not change. It will always be his unchanging nullifier value and the query. So if he wanted to vote twice for pineapple belonging on pizza, he couldn't. He can only vote once because people will be able to tell that the second vote came from the same person. And you notice as well that this hash, which is kind of this like nullifier, doesn't reveal who Weijie is at all. It keeps him completely anonymous. And you can imagine that if someone else came in and wanted to vote on the same topic or contribute their opinion to this discussion, they would also have a different nullifier, and you wouldn't know from the public looking in which one of these two messages came from Weijie and which one came from Barry. So okay, so what exactly is the code that is being executed here? So similarly to before, we're going to pass in the Merkle root and the message, and we're also going to pass in this like topic. And in the semaphore protocol, they call this topic the external nullifier. You can imagine this as just kind of the topic, this hash of like, does pineapple belong on pizza? The external nullifier allows us to say that as long as the external nullifier is the same, the nullifier hash that Weijie will generate has to be the same. So you can imagine maybe the external nullifier changes for different polls or different topics or different applications that you use. Okay, what else do we pass in? We pass in, those are our public inputs, we pass in our private inputs. This is, again, our two secrets that we don't want to share to anyone, say the ones that are on Weijie's computer, the nullifier and the trapdoor. We're going to call these identity nullifier and identity trapdoor to differentiate them from the external nullifier. And the Merkle path that we had before. Okay, and then what is the thing that the ZK proof is actually going to assert? The ZK proof is going to assert our Merkle path calculation is correct. So the same thing as before, we just calculate the leaf, and we verify the hashes match up to the root. And the second thing we're going to assert is that this nullifier hash is calculated correctly. And it's going to be a public output of this calculation. So what precisely is this nullifier hash calculating? It is saying, OK, our nullifier hash is going to be the hash of our secret identity nullifier, remember this value that we have, and this external nullifier, which is the topic that we're commenting on. And so you can imagine that, like we were talking about before, as long as this topic is the same, there is no way that Weijie can change this hash. And so it'll correlate him across all of his votes, or all of his messages. And so you can imagine that in a voting app, you would just take the first vote. In a messaging app, you would say, someone commented all of these things, and they're all the same person, and they're all from this group, but we don't know who they are. Cool. And so kind of maybe more answering, OK, what exactly, where does this proof go? So Weijie can send a ZK proof. This can be sent to a smart contract. This can be to something running on everyone's computers. It can be a peer-to-peer network. It doesn't matter. They send the proof they generated. These are the elliptic curve points that allow you to verify the proof. They send the Merkle root, which is, remember, one of the public inputs, the message, another public input, and the nullifier hash, which is their public output. And this is the output of running their proof function. And so now you can imagine that if Weijie wants to publish this yes message on the database, it'll come with this nullifier hash 1. So in the database, it'll have a mapping of nullifier hash 1 to the vote yes. And nullifier hash 1 keeps Weijie secret. And if he tries to post again, it'll check that nullifier hash already exists and won't let him post again. Or if it's in the case of a message board, we'll be like, that's the same person as before, even though we don't know who it is. And Barry can come in and use his own nullifier hash and get added to the database himself. OK, so are there any questions on the semaphore construction? Yes?
So it seems like for hash you need actual randomness. You cannot just get away with collision resistance, because otherwise then nullifier would be if I assign the related messages, maybe you can figure something out.
Yes, precisely. We want to ensure that we need all the properties of the hash function here, not just collision resistance. That's correct. Great. So far we've been talking about sending messages to a group. But you might imagine that maybe you want to use anonymity for something a little bit more. And so this was what Tornado Cash tried to do. They basically allow you to send money to an anonymous account by attaching a ZK proof of membership with each withdrawal along with the nullifier. So OK, we're going to have to unpack this a little bit. But the idea is there might be a case in which there is some, say, pool of money, this dark pool in the middle, and this dark pool has only two operations. 1 ETH can be sent in, or 1 ETH can be sent out. You can't send in half an ETH, you can't take out 2 ETH. It's just a single atomic value is put in and a single atomic value is taken out. And you might imagine that maybe people want to use this as kind of a mixer. Like people can deposit into it, and you want this dark pool to operate autonomously so that no one is controlling and no one can break the anonymity if you want to withdraw from that dark pool later to an unlinked account. And so Tornado Cash was a pretty big improvement over the state of the art, which was like Bitcoin mixers a couple years back, which you kind of have a single individual who knows the status of everyone who's depositing into the dark pool and depositing out, which is kind of a failure case. And Zcash allows you to do a very similar thing. So what precisely how would someone use Tornado Cash? They would send 1 ETH into this dark pool, and they would publish this, just like the identity commitment that we were talking about earlier, this hash of nullifier, and instead of trapdoor, we're just going to call it a secret. So the 1 ETH gets added to the pool, and their identity, this hash of nullifier secret 1, gets added to the Merkle tree. And other people can join the pool, and they can send 1 ETH, and they add their hash of nullifier and secret to the deposit list. And you might see where this is going now, that if someone has done a deposit, they can later do an anonymous withdraw by just proving that they were part of the group that deposited. So how exactly would this work? OK, so similarly, we're going to go through the code here. We've seen all of these before. The one small change is that instead of a message, we have a recipient public key. So this is where, let's say, alexis.eth put in 1 ETH. They want to withdraw to this completely unlinked account, the recipient public key. And so this is some key that Alexis can generate on her computer by just taking an elliptic curve operation. And this key, no one knows that it's tied to Alexis. But Alexis knows that this is her key, and that the money is going to go to an account that she owns. OK, but other than that, we have a similar kind of thing. We are going to have the Merkle root, this message, the recipient public key, and the nullifier hash, the output that we discussed earlier. And our private inputs are going to be the nullifier. So remember the first half of your secret commitment, the secret, second half of your secret commitment, and the Merkle path, which has to remain private or else you'd be de-anonymized. OK, so what is this logic asserting? So we've already seen the Merkle proof. We know that the leaf matches hashing the nullifier and secret value, and we verify the Merkle path holds. And then, in fact, this nullifier calculation is even simpler. Instead of the topic, there is only one topic. The topic is you're putting 1 ETH in and out of this pool. So we don't need this topic value anymore. We can just say, OK, forget hash of nullifier in the topic. We're just going to hash the nullifier value. And so the person can deposit once with their nullifier and can withdraw once with that same nullifier. And so this is almost like an even simpler version of the semaphore scheme. So how is this used? Well, Alexis would call this proving function, and the output of that proving function would be these 4 values. It would be the ZK proof, so these are the elliptic curve signals that can verify that the asserts hold, the Merkle root, the recipient, so in this case that 7AB89 that no one knows is Alexis, and the nullifier hash, which remember was the hash of the first half of their secret commitment, kind of hash of N1. And it'll get sent to an on-chain contract. So what does this on-chain contract verify? It verifies the ZK proof signals hold. So in fact, these asserts that we asserted in the previous slide hold correctly. It'll verify this Merkle root matches. So it'll manually check this public output to the current Merkle root in the data and make sure these values are the same. It'll verify this nullifier hash hasn't been seen before. So far, our dark pool still has our 5 coins, and no one has withdrawn yet, so there's no withdrawal nullifiers. So this isn't a problem yet. And once Alexis withdraws, their nullifier hash will be added to that list, blocking them from withdrawing again. And the final thing that happens is, as long as all these checks pass, the money can get sent to the recipient. So you can imagine that as soon as the proof goes to this contract and the contract runs, the 2 things that happen are the nullifier hash is added to the withdrawal list, and the money is sent to Alexis's anonymous account. Now, if Alexis tried to withdraw again, say she deposited 1 ETH and wanted to withdraw 2 ETH from this pool, the issue is that their nullifier hash wouldn't change. Remember, it's just hash of n1. And so at this step, where we verify the nullifier hash hasn't been seen before, we look in the withdrawal list. We say, have we seen our hash of n1 before? We do. That's the same. And so it would block at this step, and the money wouldn't be released. And so you can kind of see how this kind of maintains the invariance of being able to deposit and being able to withdraw only the amount that you deposited. But yet, note that nowhere on this slide does it say Alexis or alexis.eth. Like, this entire process can happen completely anonymously. Cool. So are there any questions on Tornado Cash before we move on? Yes?
How are the nullifiers selected? Is there anything
Yeah.
that constrains me from like generating a bunch of transactions with random nullifiers to collide with someone else's nullifier? Like, I'm trying to figure out what the constraints are on the generation of those values.
Yep. So the nullifier is a completely random 256-bit value that you'll generate on your own computer. And so colliding with someone else would have a probability of 1 over 2 to the 256. And either way, you don't know their secret value, so you can't even verify whether it collided or not. And yeah, because it's random every time, there's no like structure to that value at all. Cool. So you can imagine that now if Betty comes in and wants to generate the ZK proof, they generate their own proof. They have a different nullifier hash. So it's not going to match nullifier hash 1. And they can withdraw themselves to their own account. Yes, you had a question.
How does this work in practice in terms of different amounts? So maybe Alexis is sending a certain amount that isn't just one.
Mm-hmm.
How do people not like match up the amounts? Or can you say more about how this is used in practice?
Yeah, so in practice, there's like a couple things you have to watch out for. So this specific database that's stored on the blockchain is the 1 ETH pool. And you can imagine there's kind of someone has cloned all this identically, and there's a 0.1 ETH pool, and someone has cloned all of this, and there's a 100 ETH pool, et cetera. And so let's say you want to deposit 301 ETH. You would send 3 deposits into the 100 ETH pool and 1 deposit into the 1 ETH pool. And then later, you would do 3 withdrawals from the 100 ETH pool and 1 withdrawal from the 1 ETH pool.
Oh, so truly everyone sends the same amount always to the
Yeah, you have to, because if the numbers were different, then you'd be able to tell, obviously, that was the person that deposited. Yeah, yeah, that's a great question. And there are some quirks with this. And for instance, like, if someone deposits and then 1 second later withdraws to their anonymous account, you can clearly tell that that person was probably the same person that just deposited. Or if someone has deposited 301 and has done 3 deposits of 100 at the same time and 1 of 1, and then later you see 3 withdrawals of 100 and then 1 of 1, you're like, well, that's probably the same person. And so people have used these kind of heuristics to sort of break Tornado Cash, and there's kind of a proof of concept called Tudela that you can see that does that. And so it's a little bit imperfect. You have to make sure you're kind of careful of withdrawing them at different times, and making sure you're using the right amounts. So there are some kind of operational quirks here, but we'll discuss ways that you can get around this. So okay, so let's go over what we've seen so far. So we saw a bunch of the set membership stuff. We saw the signature verification, and then we saw nullifiers. So what we haven't done yet is combine these. We haven't combined the signature verification from Hayanon with our new way of doing this nullifiers to avoid double spending. OK, so what if we kind of want to mix these? We want to do signature verification, and we want to have a nullifier. So this is where stealth drop comes in, which is kind of, you can imagine this as the naive way that you would combine signature verification and nullifiers. And it didn't quite work. And I'll go through the broken construction and explain why it didn't quite work. And then we'll try to go over how one could fix this construction. So what does stealth drop let you do? Well, this project let you claim something called an airdrop. So some people raise their hand if they know what an airdrop is. OK, this is basically everyone. So the idea is that if someone is doing an airdrop, there's a protocol who's going to give some amount of money to all of its users. And so instead of the user participating in the sign-up phase, the protocol or the program is going to do the sign-up phase and say, these are the people that are eligible to claim this money. And then when people withdraw, they attach a ZK proof of membership along with a nullifier. And so you can verify that, oh, they're in the set of people that were chosen to withdraw, and they can't withdraw more than once. So it seems like we can just mash together the primitives we've seen so far, and we should be good. OK, so how does this flow work? We have the airdropper contract. So this is, say, the protocol. And they've chosen a Merkle tree of eligible addresses that can claim this airdrop. And there's the empty nullifier list of people who have claimed it so far. And let's say Adyan is on this list. He's decided, I am this value in the Merkle tree. And so in order for me to claim to my unlinked account, AD829, etc., I'm going to provide a proof of ownership that I, in fact, know the private key that is in this adyan.eth node. I'm going to do that by just providing a signature. If I can sign a message, then I must have had the private key. And so this ZK proof, remember, very similar to stuff we've seen so far, the Merkle tree, the signature proof will just get sent to that anonymous account. And then this anonymous account, AD829, can send Adyan's proof to the blockchain. It'll check, does it appear on the nullifier list, yes or no? And then if it doesn't, it'll unlock the reward to that address. And on this side, there is no indication that this proof came from Adyan. There's only the anonymous signals and the nullifier. So OK, so in code, what would this look like? So let's say Nolan and Adyan are in this tree, and Nolan is going to generate a ZK proof of withdrawal. Well, OK, what are the arguments that are going to be passed into this proof? Well, the Merkle root of our airdropping tree, his specific public key. So in this case, I use Nolan.eth as a stand-in for 0xD56, whatever the address is, and a signature of some known message with his secret key, and the Merkle path. OK, so the inputs look very similar to what we've seen before. We have our Merkle root. We have our public key, which we don't want to reveal. We have the signature, which we also don't want to reveal, because if someone has a signature, they can figure out which public key signed it. And they have the Merkle path, which, again, we want to keep secret. So now what could you do? What is the logic that is actually being proved in the ZK proof? Well, logic is the Merkle path we've seen before. We just check that the public key is, in fact, in this Merkle tree. And then we verify the signature, again, with the public key and the message. So this message here would verify that this is a signature on the message stealthdrop.out. And then we would have the nullifier hash calculation. Now, the naive way to do this nullifier hash calculation is you just hash the signature of the message. So this is a little bit different than the nullifier calculation we've done before, but let's think about it to give us the properties we want. So the hash of the signature of the message would allow us to say, OK, if I have only this nullifier hash, I can't figure out what the signature is because I can't reverse engineer this hash. If I can use a deterministic signature, I potentially can't generate more than one signature. And this should be enough for me to say that I can withdraw once. And if I try to withdraw again, I'll sign the same message. And so theoretically, I can get the same signature. And maybe the withdraw will stop me from withdrawing again. You can imagine that after running this proof and sending it to the chain, maybe the nullifier hash gets added to this list. Now, the problem with this is that deterministic ECDSA signatures don't work quite how you think. And so what happened is, we published this MVP, and luckily there wasn't any money in it. It was experimental code. We got a DM saying, hey, I think there's a way that deterministic signatures don't quite work here. And the reason it doesn't work is because deterministic signatures aren't provably deterministic. The way deterministic signatures work is they just seed randomness from your secret key. And they use that to generate a signature. So if your secret key stays the same, you seed the same randomness, and you generate the same signature. But the thing is that someone with their secret key can just throw in a different seed and generate a new signature. And now they have another signature for the same message. And it's not the deterministic one, but without their secret key, we have no way to tell. And so it turns out that even if something is called a deterministic signature on ECDSA, people can go in and generate non-deterministic ones. And this would break the scheme. Why would this break the scheme? Because here, someone can just pass in, do all the same arguments, but a different signature. They will get a different nullifier. And then when they withdraw, it'll seem like they're a new person, and they'll withdraw to their unlinked account again and again until you drain the entire pool. OK, so clearly getting this nullifier thing is pretty critical. So how would we do this? So let's kind of just do a quick recap before we move on. So we've seen our group membership primitives. We've seen signature verification. And we tried to combine them in the naive way, and it didn't quite work. So we're going to try to explore a slightly more smart way to do this. And to do that, we have to kind of go back to, OK, what are the properties of these things that we want? Like, what exactly is the properties of this nullifier? And what are the properties that Ethereum gives us? And how can we combine these in a more clever way? Okay, so we need our anonymous nullifier to be unique. We want it so that everyone can have a different nullifier. Okay? We want it to be deterministic, but actually deterministic. Like there should only be one way for someone to generate this message, this nullifier. And if they do it again and again, it should be the same. We want it to be verifiable without the secret key. So this is a kind of a new thing that we want with Ethereum that we maybe didn't want before. Because in Semaphore, we just kind of paste in our secret into the ZK proving logic, and it does the ZK proving logic, and we're totally OK with that. But with Ethereum, you don't want to paste in your secret key into even a ZK proof, because something as innocuous as copy-pasting the secret key on your computer could leak it, and someone could steal millions of dollars. And so we kind of run into this issue where we're trying to combine the thing that holds all of our money and all of our identity, and these ZK proofs. There shouldn't be a way to have all of our money and identity stolen if we try to use this scheme. You don't even want to enter that territory, so we just say we don't want to have the secret key to verify this. And in practice, this is also necessary because a lot of people have hardware wallets, and hardware wallets, there's no way to get a secret key out of a hardware wallet. So we can't copy-paste the secret key around and do the naive thing that we did earlier with Semaphore and ZK message board. And one final interesting property that we might want is this non-interactivity. So remember we talked about the tornado cache leaks, where it's possible that if you were kind of not careful with the way that you deposited and withdrew, or you didn't wait enough time, someone could correlate who you were. And this is because there's kind of two steps of interaction. There's the interaction where you sign up / deposit. There's the interaction where you withdraw. But if we have these two steps, you always run into these problems, right? So maybe you could do something like Semaphore for this, where for stealth drop, you sign up for a Semaphore key first. Those get put in the Merkle tree, and then you claim the airdrop. But this requires this kind of two-phase thing. And with the two-phase thing, it's possible, if you're not careful, to extract this, this anonymity and strip it. So in the ideal scenario, we kind of want a system that doesn't have custom signups. And you can just do this off the bat. And so you can imagine that there's no opt-in to the system, right? So if we have non-interactivity, then today I could say I'm going to airdrop to all 400 million accounts on Ethereum. And I could do it. They wouldn't have to sign up for my thing. They would just be automatically entered. Cool. So with these properties in mind, let's try to go through maybe some dummy constructions. And go ahead.
How do you describe the fact that only the person who it belongs to should be able to compute? Right? Nobody should be able to compute my
Yeah, exactly. So it's kind of like private anonymous. It's kind of, I put anonymous in the title, but yeah, maybe it should have additionally been like a specific property. But we want it to be completely anonymous. No one can correlate my nullifier back to my identity. It should be private anonymous. So to get an intuition for this, maybe let's try to go through some ideas that may or may not work and get a sense for why they will or won't work. And maybe that'll let us build to a scheme that would work. So we already explored deterministic ECDSA signatures. Even though it says deterministic, it's not quite deterministic in the sense that someone else could generate a fake one and you have no idea. It's not like verifiably deterministic per se. OK, well, here's one example. What if our nullifier was the hash of our message and our public key? Well, if someone, this kind of keeps you anonymous. If you have this hash, you can't reverse engineer and figure it out. It's deterministic, so if I have a public key, it'll be the same every time. I don't have to use my secret key in it. It doesn't require interactivity. Anyone else can compute the hash of message public key. So maybe one good thinking exercise here is, why does hash of message comma public key not work as a nullifier?
Sure. Private, like anyone can compute it. Like everyone can.
Exactly, right? So if we had this as our nullifier, then anyone can go through all the public keys on Ethereum, compute these hashes, and see, oh, that one matches that hash. And we've de-anonymized the person.
How many public keys are there?
I checked like 2 years ago or something, and it was 300 to 400 million. So it'll be a pretty fast computation. You can do it in like, I don't know, less than $1 on AWS probably. OK, let's try a new one. Hash of message comma secret key. So the first thing is, well, this does copy paste the secret key in. So we've already broken one of our properties, but let's try to think about the other properties. It's unique, so everyone will have a different one because everyone has a different secret key. It's deterministic. My secret key doesn't change. The message won't change. It's non-interactive in the sense that if someone has published this, I can kind of go in and claim with this as my nullifier and do the public key membership. And so it seems like the only issue with this is that we're kind of pasting in our secret key. There's no way to generate this without copy-pasting around our secret key. OK, so let's maybe try to combine these a little bit. And so we get this scheme, which is hash of message comma public key to the power of secret key. This is kind of a little bit of a weird construction. Like we've kind of mashed together these two things and introduced this weird exponent. What are the properties that this gives us? Well, OK, so with this, we fix the problem with hash of message comma public key. Not everyone in the world can compute this. You need the secret key to compute this. And so, OK, we solved that. It's non-interactive in the sense that anyone can kind of publish the Merkle tree of public keys, and this can be my nullifier, and that's totally OK. I don't need to sign up first. It's unique and deterministic. It's different for everyone, and it's computed the same every time, as long as the message doesn't change. And the last property, verifiable without our secret key. So one might imagine that you need the secret key to verify this was calculated correctly. But it turns out there's some clever math we can do such that we can verify this without having the secret key, in a similar way to how one can do various elliptic curve operations and verify a signature that someone generated with their secret key without having that secret key. So just to summarize the properties we're looking for a deterministic function of the user's secret key that can be verified with only their public key, yet keeps them anonymous.
Can we just combine the first two, like use a deterministic signature as part of the hash computation? Nobody can compute it, and like everyone.
So
Stock will be able to verify it.
So are you talking about the hash of the deterministic signature?
Like in the second line,
Yes.
also add in like deterministic signatures as one of the arguments.
OK, so let's try that. So hash of message comma public key comma deterministic ECDSA signature. So the thing with this is that I could still do the thing that we did before with stealth drop.
Sure, yeah.
Yes, exactly. I could just keep generating new signatures, and it's kind of, you can't verify it was the verifiably deterministic ECDSA key. So OK, so how can you solve this? Yes, go ahead.
Why does the last example avoid the copy and paste issue of the secret?
Yep, so this is the thing that I'll explain in 2 slides, which is the exact math behind how we can do this without having the secret key. It's a little tricky. But the high-level thing is that by deploying a new kind of deterministic signature on Ethereum, we can potentially get all the properties that we want, using your pre-existing Ethereum secret and public keys. OK, so this slide is going to be extremely mathy. It's going to be the most mathy slide of this whole presentation. And so I don't expect most people to understand this on the first go-around. If you guys want to go over it in more detail, I'm happy to kind of go over it afterwards. Also, slides will be online. I'd kind of recommend going through it slower there. But basically, what I've done is I've color-coded all the values that are the same. So all the public key values will be blue. All the message values will be yellow. And I'll point out a couple key things to notice in the complex math construction. OK, so one key thing is the public value at the top, our nullifier, is the value I was talking about earlier. It's a little bit hard to read, but that's the hash of message comma public key to the power of secret key. This value will be public. It'll be our kind of nullifier hash. And then we'll have all of these private values that are also computed by our wallet with our secret key. But these values, the important thing to notice here is that even if you know C, S, pk, g to the r, hash of m comma pk to the r, the important thing to notice here is that having all of these values does not allow you to reverse engineer someone's secret key. This is kind of the interesting thing to notice here, is that you can kind of do the mental gymnastics in your head, but there's no way to get someone's secret key out of just these 5 signals. And to just briefly go over what each one is, C, so by taking a hash has this interesting property that it kind of enforces like an order in the sense that I must have known all of the arguments to the hash function before I knew the output of the hash function, because of the way the hash function works. Right? It maps a bunch of kind of values to this completely random value. So if I change any one of those values, that would change the target value. So it kind of enforces that I had to know these values and have committed to them before I knew C. And so this S value, which is R plus sk times C, and R is just a random number we generate, is I must have known secret key, which I committed to, before I knew C. And in addition, I must have known R before I knew C, because R is also committed to as part of this hash computation. And so you can kind of imagine the intuition here is that without understanding exactly what's going on, it's still important to notice that one must have known the secret key going into that computation. So kind of in a way that a signature, we use a signature just to verify that someone knew the secret key, we can use this combination of C and S values to verify that someone knew the secret key because of this kind of ordering property that hash function gives you. And then, OK, what is actually being verified in the snark? This is also a little bit complex, but the idea is you can, the way we get around pasting in the secret key is that because elliptic curve operations allow us to kind of operate on just like the exponent of the thing that the generator is being taken to the power of 2. So we can kind of take our public key to the power of some of these numbers and some multiply together. And so for instance, in this computation, R plus sk times c, if we take sk to the power of c, this becomes g to the power of sk times c. And if we divide this, these cancel out and give us back g to the r. And so we can kind of do operations on those values. And the kind of intuition here is we can do operations on the values that we're taking the exponent of without knowing them, without leaking them. That's kind of the nice property that we get here. And it turns out that if we do all of these verifications, it in fact verifies for us that this nullifier was calculated correctly, that someone must have known the secret key in order to calculate it. But in these calculations, the secret key is not present. And in fact, just from these calculations and these signals, there's no way to get someone's secret key back.
How is this related to the Schnorr signature?
Yes, it's very similar. It's inspired by Schnorr signatures. It's inspired by, if you've heard of EDL signatures, it's inspired by Chom Pedersen.
Can you phrase this in terms of Schnorr, or is it something new?
OK, I would have to pull up the definition of Schnorr, and then we can kind of go line by line and compare. We can do that afterwards. It'll be a pretty fun exercise to have up. But yeah, let's do that. That'll be fun. But yeah, it's very similar. It's almost the same thing. It's just this will work on your Ethereum secret and public key, versus Schnorr signatures, the original construction, I think kind of requires, is not quite exactly the same thing. OK, so using this scheme, where we define this kind of new ZK proof that generates our nullifier and proves it was generated correctly, how would we actually edit stealth drop to work? Well, what we could do is Nolan could generate this new ZK proof. And what this new ZK proof does is the things that are passed in are like before. We have the Merkle root, we have our public key, we have these CNS values. Remember the values that are output by the wallet, the private values. These will be kept private. So you can see there's kind of the new private inputs. And we have this new plume signature of message. So we've called this kind of signature scheme like a plume signature. You can imagine it as like a verifiably deterministic signature. Like we can verify that it was deterministically generated. And this plume signature is exactly the calculation we saw before. It's the thing we call the nullifier. It was the hash of m comma pk to the power of sk. And the Merkle path, our good friend from before. OK, so what are the new things that are going to be verified in this proof? Well, instead of the ECDSA signature, we're going to verify the plume signature. This plume signature is going to be the exact verification step that we saw on the previous slide. We're going to just copy paste exactly this check inside the ZK snark here. And so those kind of 4 checks that we were doing, so we copy paste into this verification step. It's going to verify that this value, which is the hash of m comma pk to the power of sk, in fact uses the correct message, was calculated correctly. The user must have known the secret key. But this plume signature of message is completely unique. And so we can just directly make our nullifier the signature that we just defined. Right? The nullifier, I kind of referred to it as nullifier in previous slides because that's exactly what it is. It kind of functions as both a signature and a completely deterministic nullifier that keeps the person signing secret. This is quite interesting. We can kind of do the signature verification and keep the public key private. And people can still believe that it came from one of the values in this Merkle tree.
Question.
Yes?
So CS and the signature are generated by the wallet, but if I leak them, I don't reveal anything.
Yes. Even if you leaked C, S, and the signature, you would only reveal your public key. People wouldn't be able to figure out your secret key, which is kind of the key difference from just copy-pasting your secret key around.
So you can even delegate this proof to someone else.
Delegating the proof to someone else would mean that they would know your public key.
Sure.
Yeah.
Like if you had a hardware
Yeah, yeah, exactly. So the way you would have to do this is kind of the CS and signature, which requires the secret key to compute, would have to be part of like the hardware wallet spec. Yeah. So we're actually kind of working on that right now and trying to put like this specific scheme inside like hardware wallets like Ledger and things. And we're working on like a MetaMask implementation right now. There's a fellow named Richard who's doing a great job of that. Cool. Okay, so let's kind of go back to our roadmap and kind of reorient ourselves. So we proved very simple group membership. We saw set membership and how to use Ethereum and signatures. We switched over to nullifiers. We understood how nullifiers work in the context of semaphore and tornado cache. And nullifiers are present in a lot of different places. You'll see like a lot of the ZK proof systems, especially the ones that deal with money, like Aztec, Zcash, they all have their own version of nullifiers. We went over how we could do this on Ethereum directly, why something wouldn't work, and a way to fix it, which is pretty invasive. You have to make fork to the wallet. You have to add a new signature scheme to Ethereum. But if done, then could give you this ability to do anonymous proofs with nullifiers on Ethereum. And now we're going to switch gears a little bit, and we're going to talk about how group membership or proofs might look in the wild. So far we've talked about people kind of generating their own identities or using their Ethereum identity. But how can we have these kind of ZK primitives used like with existing identities, like maybe your email address or something? Cool. So the first thing we're going to go over is kind of ZK email. And the idea is that your email implicitly has like a signature inside of it. When someone sends an email to someone else, there's a signature generated by the sending mail server of that email being generated correctly. And this is how you know that if you got an email from sampriti@gmail.com, that it actually came from sampriti@gmail.com and not from someone else. And your email inbox does this behind the scenes. You hardly even know about it. So to kind of dig into how we might get interesting ZK primitives out of this, we have to dig into exactly what the signature is doing. So what precisely is a signature scheme used in this email signature scheme called DKIM? It is the RSA signature of the SHA-256 hash of all of the things in the email, the from, the to, the subject, the body, and that is signed with a key. So it can be signed with MIT.edu's mail server key, which everyone knows the public key of. And just as a quick checker, can people raise their hand if they know roughly how the RSA signature algorithm works? Okay, that's basically everyone. Great. Cool. So what you can imagine is that maybe we can do a ZK proof on top of this. So if we wrap this entire check in a ZK proof, what we could do is if a user can provide the signature, which is the email header, to the ZK proof, you can verify that an email was sent from someone to someone else. And this will allow no one to determine, if it's all in ZK, who was the person that sent this message or what the message was or who it was sent to, unless the user wants to reveal that as part of the ZK proof. And there's a couple of quirks here. Some people don't have all the fields. Sometimes the keys are a different number of bits. Sometimes some specific emails aren't signed. By and large, 99% of the emails in your inbox will have this kind of a format. So okay, so what exactly is a proof? It's a little too complex to write in the CIRCOM code version that we were doing earlier. So let's maybe just try to go through what exactly the public and private inputs are and what the circuit is checking. And kind of what are we trying to prove here? So imagine the thing we're trying to prove here is that I received an email from verifiedtwitter.com that has my Twitter username in it. And I'm going to extract my Twitter username from that and just mask that out and prove that this is my Twitter username without trusting any server, without trusting anyone in the middle. And I can do anonymity checks on this. I can say, if there's some database that maps Twitter usernames to the number of Twitter followers, I can do a ZK proof saying like, I'm not going to reveal anything to you except that Twitter sent me an email proving that I own this Twitter username, and that Twitter username has at least 100,000 followers, but I'm not going to tell you anything else about it. I'm not going to tell you my username, I'm not going to tell you my email address, I'm not going to tell you my name, nothing else. And so how might we do this kind of a construction? Well, the public inputs that we would have could be the sender domain. So maybe this is like verifiedtwitter.com. It would have the RSA modulus. So this would basically be twitter.com's public mail server key. This is basically the RSA public key. it would have the masked email body. So it would say, look, in this email body, I want to reveal nothing in any of the headers or the from or the to or the body except for this small regex match of my username. And the private inputs here would be the actual signature from the mail server. So if people had the signature, they would be able to tell potentially, well, one is that the mail server that sent to the email would be able to figure out who you were if that signature were public, because they know all the signatures that they produced. So we have to keep that private. The length of the data, so various metadata about it, so that kind of in Circon we can go in and we can, or any ZK circuit language, we can go in and kind of fix these lengths and say, okay, this message was 10 bytes long, but that message was 20 bytes long, and the proof will work for up to some maximum number of bytes. The raw message data, so this is the actual raw email body of what is happening, so we can actually verify the signature, right? Because if we want to verify the signature, we have to go back to our DKIM formula. We have to calculate this entire body, we have to calculate this whole subject, we have to calculate this entire SHA-256 hash, then we have to calculate and verify the signature on top of it, and only then can we be sure that the signature was correct. So we need those full inputs. We need the full raw message data. All right, so now what does the ZK circuit check? The ZK circuit checks exactly that DKIM thing. It calculates the SHA-256. It calculates the RSA verification. Some great folks with ZeroXPark, Andrew and Stephen, I believe, put together a great RSA verification circuit. And it verifies that the sender and receiver domains are well structured. So this requires kind of a regex. Like you have to regex over the entire header in order to extract this from and to value. And so we kind of had to implement ZK regex inside of like a ZK circuit. And then the contract, so far we have what the ZK proof is doing. It's kind of calculating this, the DKIM, it's regex parsing and ensuring that everything is correct, and then it can mask out specifically the parts that it wants to reveal. So you can imagine an additional thing that the ZK circuit is doing, we're not specifically checking, is that it is masking the email to say, okay, we're only going to reveal verifytwitter.com, and we're only going to reveal your Twitter username. We're going to mask out everything else. So some specific regex matches. And then our smart contract is going to check that, or this can be a smart contract, this can be a front end, this can kind of be anything else, but you can verify this this kind of proof by saying, okay, the sender domain should match this verifytwitter.com or whatever other email domain we want. The RSA key that we're claiming this is signed by should match the RSA key that we fetched from the DNS. So these keys can rotate as frequently as never. It can rotate once every 2 years or something. And so you can imagine that if the key never rotates, you can just hard code it into the smart contract or whoever's checking. If it does change, you can have some client-side check that verifies the DNS get of that key matches the proof that you got. We have to be a little bit careful about kind of your DNS not getting man-in-the-middle attacked. But for instance, if the RSA key never changes, you can hard code that in, and you never have that problem. OK, so this was kind of a lot to take in. And in this proof, we verified some anonymous thing about our Twitter account. But we could also verify, for instance, kind of any other group membership of any information, any of our emails ever. And this is like a pretty powerful concept, that we can mask any email we received and only reveal certain parts of that. And it's kind of, it maybe be irresponsible for me to talk about this primitive without talking about, how we should be responsible when releasing such tech. So one example is that you kind of get this problem with the tragedy of the commons, where individuals can now spend institutional reputation that the institution didn't sign up for, and say things on behalf of that institution, right? So what we could do is we could, for instance, use this or ZKJWTs, which I'll talk about soon, to say, OK, someone at MIT.edu who proved that they had an email at MIT.edu can say something on behalf of MIT.edu. MIT.edu never opted into the system. That's pretty interesting and pretty dangerous, because you can imagine now that someone can kind of say things that they wouldn't normally say otherwise, or say things that normally they'd be held personally accountable for, and instead the institution is held accountable. The institution hurts, and their personal reputation is not affected at all. It's interesting, when you're releasing tech, you kind of have to think about how to mitigate some of these things. Yeah.
But then also take a more like optimistic lens.
Yeah.
Like, you can also potentially increase institutional reputation if like people say things that they would otherwise be scared to say. Or like you can cultivate a culture of more honesty as well, right? It's sort of like a two-way thing.
Yeah, no, that's exactly correct. Like the reason we think this tech is really important is because, yeah, there are some downsides that you should design your system around, but ultimately the thing you get from this is really, really powerful. And you know, it can make an institution more honest. You can say like, hey, I'd be scared to say this because maybe I'd reveal who I really was, but I actually think this thing in my institution, you know, maybe could be improved. And I can prove to you that I've gone through this problem because I'm a member of the institution. And that's really interesting and valuable feedback that's not really possible to give right now.
I feel like I'm missing something conceptually.
Yes.
Can't I already do this by saying something ridiculous from my @mit.email.edu account and just doing it where you would know it came from me, but since I still have my MIT email, it's still coming from the institution?
So,
For some reason, this institution let me in, and now I'm saying ridiculous things.
so you're saying instead of doing the ZK, we just kind of do this raw DKIM verification.
Or like maybe this is already an issue without the email.
So the thing is that in order to do this DKIM verification, you have to have all of the things that are in that email. You'd have to have the entire from domain, the entire to domain, to verify that whole DKIM thing properly. And so if you had a valid signature, in order for anyone to verify it or to believe you, they would have to have seen the full, without ZK, the full sender and the full from and to domains. So there wouldn't be a way for you to say like, oh, like I'm just going to send an email from my MIT edu account and say something ridiculous without anyone knowing who I am.
Oh, I mean, in terms
Or-
of the societal impact,
Mm.
maybe it doesn't matter to hide someone's identity in order for you to still damage the institutional
That's true.
reputation by people saying ridiculous
That's true. That's true.
emails.
So normally what you could do is you could just have individuals could say something ridiculous and they would harm the institutional reputation and they would also harm their own reputation. But if you imagine like how you think about this, like if there's a single individual at some institution who's saying ridiculous stuff, you kind of usually blame that specific individual who is then held accountable for their statements, and maybe you can give the rest of the institution some amount of credibility. They can say, well, the rest of the institution didn't say this, just that one person did, so I guess for now, I can kind of believe that it's that one person. So it's kind of this like personal accountability that ensures that those people, if they would say something that would really destroy the institution's reputation, they would probably destroy some amount of their own too. And so it usually prevents this kind of thing from happening in real life, although there are many cases where it doesn't. You're right. And the kind of things that we enable this like new thing, which is you don't have to spend any of your own personal reputation to say something ridiculous, which is kind of the scary thing. Does that kind of answer the question? That it kind of exists, but there's kind of some safeguard, but it's kind of like, yeah. Cool. Yeah, there's some questions with like deniability. There's some proposals that people have proposed, which are, maybe people should leak their DKIM keys, signing keys every 2 years, so that you can't do this kind of attestation for an old enough email. And that kind of thing would be interesting. It would you would still be able to do these kind of proofs, but it would have to be a recent email. And you can't say, 10 years ago someone sent me this, because that private key maybe got leaked, and so it gives that person deniability because anyone can forge a signature. There's kind of this interesting nullifier trade-off. So we've been talking a bunch about nullifiers and how it allows you to stop someone from double spending or double saying. And a natural question is, does this scheme, like the ZK email scheme, have like a nullifier built into it, right? Like, can I say this was some individual from MIT, and if they try to prove again, it was the same individual from MIT. And we could kind of do this. We could publish the hash of the signature, for instance. And because it's an RSA signature, it is verifiably deterministic to start with. But the issue is then the sending mail server, that is MIT.edu, the person that owns the private key, could just look at all their past signatures, calculate that hash, and de-anonymize you. So you kind of have this trade-off where if you want to have nullifiers, you allow the sending institution to de-anonymize you. And if you don't want nullifiers, then it's completely anonymous to everyone, which is kind of interesting. The rotating public keys can potentially cause issues if you've hard-coded this into a smart contract and the public key changes. And there's ways around this. You can have like K of n type guarantees. You could have like DNSSEC would solve this. And we're hoping to have these kind of verified DNS gets become more common. And one interesting thing is that BCCs cause a little bit of problem with this scheme, where if someone is BCC'd on an email, they get that header and they can make any proof about as if they were the person that received that email. And so the thing with BCCs is that this means that the only interesting things you can prove are things about the sender of that email saying something. And so you it's much harder to say something like, I am the person that received this email, because you could have also been some person that was BCC'd. But this still doesn't, you still can say a lot of very interesting things about the person that sent the email, which BCCs doesn't break. So there's a number of pretty cool applications here. And I'll talk about a couple. And so, one is that kind of Twitter verification thing I was talking about earlier. You can also, oh yeah, I should reload the slides. Let me, yeah. Cool. Yes, okay. Yep, from here, great, perfect. Cool, okay, so what are some kind of interesting application that you can build with this thing? Well, okay, so kind of going back to, okay, what are all the interesting emails in your inbox you can ZK proof stuff about? You can kind of do some pretty degen stuff, like you can say like, oh, I put this trade on Robinhood, and Robinhood sends you an email confirmation every time you do so. And I, in fact, did buy that amount of that stock N days ago. And because of that, I made some amount of money. And so you can kind of have like verified Wall Street bets, which is kind of a funny, frivolous example. But it points to something much deeper, where you can do a lot of other stuff. You can do the Chase bank account example. You can, for instance, prove I have some amount of money in my Chase bank account, which Chase has sent to me in plain text. And I'm going to, in ZK, prove that number is more than 100,000 or whatever. And thus, I can prove to you that I have some amount of money in my bank account. You could do like a Spotify type of thing. You'd say like, oh, Spotify sent me my Spotify Wrapped or something, and it said I was a top fan of this artist. And so because I can ZK prove I'm a top fan of that artist, maybe the artist can say, oh, if you're a top fan of mine and you can prove it, you can get some kind of special perk. And so it's kind of like, there's a lot of very interesting ways in which once you've unlocked, instead of these kind of, this group membership stuff where people are signing up and signing in, and it's very Ethereum specific, you can kind of, these examples show that you can kind of do things that are much more general. You can kind of use any email in your inbox and prove any subset of that thing. And you can kind of, I think in a sense, do a lot more real world things, for some sense of the word real world, in the sense of pre-existing identities or pre-existing information online. And you can do various things with the Twitter stuff. So the Twitter DM, you can prove you got some DM because the DMs get sent to you on your email. You can prove the Twitter username thing I was talking about earlier. We have so many of these applications. I think one team is even trying to build one of them this week involving KYC, which will be really cool. Cool. And this work is super ongoing. Like all the stuff that we've talked about is kind of like the last 2 or 3 schemes are all kind of like active research in the area of, okay, how can like group membership become more interesting? And just as recently as last week, I think Emma, Seyun, and Kaylee are probably in the audience somewhere. Cool. They adapted a lot of the ZK email code into this idea of ZK JWTs, which gets around the BCC issue and allows you to say, I in fact own this email address, and I can mask out any part of it. And so this is really cool because you can prove that you own an email on a specific domain much more efficiently. And so you can do kind of this example of the application they have on the right, which is you can prove that you own an @berkeley.edu email account, and you can prove things on behalf of Berkeley. And it's very interesting, and it's totally live right now. You can use it, and it's pretty interesting to see that this kind of technology. Normally you would have to build like bespoke integrations. You have to say like, okay, let's like integrate to Berkeley.edu OAuth checker, and okay, now we're going to mask it. And in fact, if someone wanted to de-anonymize, they could reach out to us, and we could de-anonymize them. But you get around all those issues if you can use things like emails and JWTs. So it's really interesting seeing like how rapidly this work has evolved. Like we've gone from the very first ZK message board that at least I know of was something we pushed out almost like 2 years ago. And in just a space of 2 years, we've gone from like a lot of the schemes that we saw in the beginning to ZK JWT super recently. And so the field evolves and changes super fast. And a lot of these, like I'm sure this lecture, if delivered in 2 years, would look completely different. And so there's a lot of very cool new things that are kind of happening in terms of, okay, how can one get involved in this kind of work? And I think Vivek also has a number of opinions on these kind of applications if you want to help come up. Okay, cool. Yeah. Sounds good. Yeah. So with ZK email, there's a number of kind of interesting projects we're working on. Twitter verification is a thing that we have. Like you can do the Twitter verification right now, and it generates a ZK proof on zkemail.xyz. And we're kind of working on the smart contracts to be able to integrate that with interesting on-chain stuff very soon. You can do like anonymous proof of personhood. You can prove that, hey, I received a KYC email from some people, And I can verify that this KYC email is valid, but I'm not going to tell you which person I was when I got KYC'd. You can do paper donations. We're also, we have a team working on this, which is like, you can prove that you own some email that published an archive paper. And so if someone wants to donate to, say, like papers, currently like most researchers don't just have a donation page online, but you can now say like, I can donate to this specific archive paper, and if someone can prove that they own the email that published that paper, they can claim the money. And so this is kind of interesting because removing this non-interactivity step, like allowing people to do this without signing up, is very interesting because you can bootstrap systems where you can just do a thing like this, and no one's trusted to control millions of dollars of funds properly because it relies on ZK proofs to verify all of that. Cool, so there's a bunch more theoretical work as well kind of going on in this space where we're kind of working together to improve various things with proving stacks and making these a lot more efficient. And I know Vivek knows a lot about this stuff if you want to contribute. You might want to take these mics really quick. I'm just going to, OK. You can also just speak. OK. Just speak really loudly. Yeah.
I can project. So me and Ayush collaborated on a lot of this work that has been discussed. I was involved with hand-on and a couple of other things mentioned, and we wanted to pitch some stuff that we're both really excited about for people in this room. So yeah, this is stuff that I'm a lot more involved in on the more research and theoretical side of things. If you liked the math lectures in the past few weeks, there's a lot of really great applications to real use cases for this stuff. The big area that I focus in is in client-side proving. One really fun thing is basically like, for various operations, they can be very costly to be done within snarks. And so a lot of kind of effort needs to be put into sort of either compressing them or changing your proving stack in order to actually run these on normal devices like computers or even like your phones. And so one really fun example of some stuff that we've been working on recently is basically instead of using the normal circum stack to verify various ECDSA signatures, we've basically taken some schemes from Spartan, which was mentioned earlier in a slide from Yitong, and Halo 2 with an IPA polynomial commitment, using like sort of a different elliptic curve in the back end, such that we can basically verify ECDSA signatures really efficiently. And this is super useful for any sort of identity sets you're building on Ethereum. It's going to be useful for the nullifier construction because that uses a couple of like different ECDSA operations. Another big thing is around basically, we have all these new amazing sparkly proving stacks, but a lot of them are written in Rust, and they're mostly built for like running on actual machines or like huge AWS instances. So there's a lot of work around first just like converting all this stuff into a form where browsers can use, likely WASM, and then doing further optimization work based on the sort of specific environments that WASM is running. And Nolan, who I think was here at some point, he's in the back. Nolan's done a lot of amazing work in this realm. He's converted Halo 2 into WASM. This weekend he just shipped a version where Nova can be used in WASM, or at least like this one compiler. And another stuff that's really exciting is basically using some of this recursive aggregative schemes that are coming out to combine separate proofs that you generate about yourself into one big proof. Brandon's working on Zigzagoon, which he gave a presentation on yesterday. And there's Nova, Plonky 2, all sorts of other stuff. You can go to the next one. Another big thing, I know there's some people here who do MPC. It's very likely that we think that some proofs are just going to be too large to be done on a client-side device, and the solution will almost certainly be some sort of delegation to another party. It's unclear like if that's going to be an external server. Maybe more people will just have like better compute at their homes, but we need some sort of delegation. And the idea is like we could do something with like FHE where we like homomorphically encrypt everything. We do all the operations privately so that none of your private data is leaked. But a sort of more reasonable solution, and something that there's been active work on recently, is taking your witness. So in a lot of these use cases that I used to describe, it's like your private key or your signature. What you do is you essentially secret share that amongst a bunch of different parties. They compute the proof separately on those secret shares, and then you combine them on your own. And you can basically push a lot of work to other people and not do them yourself without sacrificing any of like your privacy. Do you want to reload the slides? I had some stuff at the end.
And one note to say about why we are doing this is that, and how this relates in context of the slides, is that in all of the examples where we were doing the proofs, we kind of had we kind of were doing all of those computations on the person's laptop. Remember, they had a little computer icon that was showing it was happening locally, and all the secret information. That is maybe the secret key signing stuff, or the secret values that were passed into the nullifier, or the secret things that they were committing to with their identity, that all happened locally. And so they can make sure that their secrets were their own. And it's kind of limits you then to the computer of your own computer, which is why we want to do this kind of MPC work and be able to extrapolate those things out so that we can add even more sections to the bottom here and do even more crazy complicated stuff.
Yeah, and going back to the previous slide really quickly, like there's a lot of stuff in the space right now that basically does some sort of half-baked solution where like a server still learns of your private information, but they sort of like then generate a ZK proof from which you can then do efficient stuff. And sort of I think both me and Ayesha are very aligned, and in general I think like a lot of other folks at Xerox PARC that for a lot of this stuff, the most interesting use case of ZK is when you do it on your own device. When you yourself are generating these claims with actual meaning, and you're not trusting a separate party to do that for you. That's a real unlock of this technology that like has not been possible prior to like 2 years ago, basically. So we think that's really exciting. Some other work which is not as like sexy or interesting, but like just as important, if not even more important, is basically just getting more of this tech out into the world. Ayush, do you want to talk a little bit about nullifiers?
Yeah, so it's kind of interesting that the nullifier scheme that we discussed that allows you to do this Ethereum and anonymity stuff is interesting because in order for this thing to be useful, wallets have to support this API. And so we have multiple people I mentioned, Richard, and there's Blake and so many other people who are helping and working getting this work to like really like be into like the system that you use right now to interact with Ethereum. And so building this API into wallets, finishing up the ZK proofs, this is all active work. I'm sure if you asked me in 2 weeks what the status was, it would be totally different. Yeah.
Another big thing is just in general, another big takeaway from this talk for you guys should be that like if there's a piece of signature on some data or something, then like we can start doing stuff with it. Whether that be a signature that you generate, a signature from someone else. Like in the email case, what's happening here is a mail server is signing this data, and then because there's a signature on it, we can generate proofs about it. And so in general, we just want to have more signatures on stuff. There's an amazing team right here working on like ZK tax auditing with a really cool solution where you have like a notary who's doing the signature for you. But the ideal solution is just the IRS themselves is signing these tax things, right? The actual source of this data puts a signature that you can verify, and then you can start doing these ZK proofs. So there's no third party involved. Another related thing is SXG. You want to talk about SXG?
Yes, SXG is quite interesting. There's this kind of primitive that I know, I think Jason is not here, but kind of Jason was working with us to figure out how to get like websites and front ends and things like that onto ZK. Like so far we've only talked about data. And it's very interesting that sometimes if your website is hosted on an edge compute cluster that is not the original data center, the way that you know that your website is still valid, even if it came from a different cluster or a different computer, say one closer to you on the edge, that HTML, like the raw front end, is often signed by the website's public key. And so you can actually verify that, say, the front end of a website is in fact the correct front end that you should be viewing. And not just that, is if you throw that in ZK, you can verify any subset of that. You can say, the New York Times published this headline. And you can prove that by showing, look, here's a headline, and here's a website from the New York Times, and you can verify that it's signed with the New York Times public key, which anyone can see. And so you can do a lot of very interesting stuff with, like, for instance, trustless oracles, where you can verify any of this data to any extent.
Yeah, and then just more broadly, like I think this tech is rapidly evolving and is changing like month by month. And a big part of like stuff we'll need to do to just get this used more is just educating and preparing different groups of people who could benefit from this. Ayush mentioned something about spending institutional reputation. That's one big thing. It's like, if we make an MIT bot where people can talk shit about it, or not talk shit, can say what they want about MIT, then, it is also, I think, at least I strongly believe that like it is also a responsibility to prepare MIT for this, to let them know this is happening, and to get them involved with how we moderate and sort of, have this forum be a useful thing. Because it's very easy for these things to just, devolve into like really awful like, hate speech or just like very useless like spammy feedback. And then another thing is like, getting these proofs sort of on other platforms. Like it'd be amazing if one day like on Twitter you're scrolling through and you can see ZK proofs of validity from like the New York Times, or like this came from an actual journalist with like this set of reputation. And we just need to talk to these folks and get them using these ZK stacks and get them thinking about like, oh yeah, like I can use this in my stuff. And so there's a lot of work there. Brian and the Xerox PARC folks have been doing so much to educate more people on this. So there's a lot of good stuff there. And then finally, really quickly, just like some fun product stuff that's coming up. Two things that I'm really involved in are like hand-on and hand-on extensions. One thing is basically this app idea called Cloak, where essentially like it's a group chat extension to different things like Discourse, which is a forum used by a lot of different places, or Discord or Telegram or WhatsApp, basically allow members of specific group chats to sign up. And then you sort of add this bot to your chat that is like this anonymous voice. And any one of you in this group can then go to this bot and then post various things. And so you can imagine, like, even in like a very, so you can think of this in orgs, like in a club or something, you have this new place where you can sort of say things about the club that you're thinking about within the group chat. But even like in a really good friend group, like if you really trust your friends and like you really think they have your best interest in mind, like it could be really interesting to have this anonymous voice where you can speak your mind or say something that's like maybe harder to say directly from yourself, but is still net good for everybody. And so there's lots of extensions here that I'm working through and would love to work with other people on. And the main thing we're really excited about is that instead of using like Ethereum signatures, we want to use like Face ID and Touch ID. It turns out that on basically everyone's device in this room, you already have the ability to make signatures using like various like Face ID or Touch ID things. This new protocol called WebAuthn. And so we're looking to, it's a shame because it's an amazing technology that a lot of people put a lot of work into, but it's not getting much use. And we think that for this sort of ZK and anonymity work, it's a great sort of place to start. Another thing is hand-on in-person. You guys are going to see this by the end of the week, but basically like another fun thing is to have these anonymous feeds like in actual events and stuff. So for various conferences, I've built basically these different feeds for people to post to and talk about the event, and they've been pretty successful and pretty fun. And for this last class, just because we sort of have to, we're teaching about ZK, so it only makes sense that whatever feedback we're collecting will also be in ZK. So I'll set all that up by the end of the week. We'll make sure that you guys can give very anonymous and honest feedback using this technology that we're learning about.
And the kind of important thing is that you guys can definitely get involved in this stuff if you're excited about it. Like if any of these things sound interesting to you, like I don't know, maybe you're really passionate about the fake news on the internet and you want to reduce it, or you're excited about these applications. Like there's a ton of really interesting work, and definitely reach out to us or anyone else to work on this kind of stuff. There's a lot of really cool, fun projects.
One final slide is, we talked about anonymity for organizations, just preparing institutions. One thing I've been really excited for a long time is how this technology will allow people to express themselves better, but also sort of in artistry and in creativity. So basically, one exciting thing I want to do is to have guilds of writers who have reputation for various things, whether they're journalists in different places or they have a very long blog or something. You make these anonymous guilds where people can post to this one feed, but it's sort of private who's actually posting. And it'd be really interesting to see what sorts of art and what sorts of expression people are able to do in these more well-structured forms, because it is still private. Maybe you can say stuff about yourself that is harder to, or you don't want to admit, but it's still useful and artistic and beautiful. And then for governance stuff, I know Yish has a lot of cool ideas on this.
Yeah, so there's a lot of really interesting stuff you can do when you kind of are allowed to straddle the line between full anonymity and full identity being revealed. One example is you could do something like, voting that's pseudonymous. You could say maybe if, you could do this in a governance forum where, for instance, someone in the US Congress could be I can prove to you, I'm a member of the US Congress, I have the US Congress email, I can prove to you I'm a Republican, but I believe this thing, or I have this opinion on this bill that goes against kind of what Republicans would normally do. And so, if half of other Republicans also said this, then my vote would automatically switch to yes, instead of no or something. And so you can make these really complex, interesting statements about the way that you actually believe things, and you can do it with some amount of anonymity or pseudonymity. And that makes interaction between people or governance potentially much more complex and interesting than it currently is, and unlocks a lot of really new possibilities for coordination, which is very exciting to see. And kind of, it allows things, instead of being ideologically bent by, say, one very vocal person, to be more of a combination of all of the people in that group. And there's a lot of really great things you can get out of this kind of group membership or discussion tech.
That's the last slide.
Cool.
Okay. Just to add on to that a little bit, I think it'll take a while before our actual U.S. Congress ever use some of this tech, getting some 60-year-old white men to learn how to use the ZK programs. Not looking reasonable anytime soon. But there's lots of local governments who are really willing to try these new experimental things, and it's a lot of this work is a lot of just we just need a lot of folks to be on the ground and to be working with different people to get this stuff used. Because I don't know, some city government in Miami or something is probably down to try this, or some random small country somewhere is wants to have better governance and wants to feel new and experimental. So even though this stuff feels very far away, there's like lots of small things to do now where like not a lot of people are focusing on it that will add up immensely over time. So.
Cool. All right. Exactly 3:31. So we nailed it. All right. Thank you guys for coming. If you have any questions, we'll be here.
Oh, also, if you want to talk about any of this stuff, DM me or Ayush on Discord. Yeah.
Are you guys will be